I'm going to talk about some signals and systems that are relevant to communication system. So in this chapter, there are a few major topics. I'm going to look at a few types of signals, a few types of system. All right, then we're going to revise the definition for signal energy and power. Remember that one of the important resources in communication system is the power. All right, so we take a look at how the signal power is being defined. So that in future, when you're required to calculate power, you know what formula to use. And also, we're going to look at or revisit the unit impulse and steps signal. All right, then we're going to take a quick look at convolution theory. Yeah, because for the signal processing part of this course, we're going to use a lot of convolution. And also Fourier series and Fourier transform. Yeah, Fourier series is useful in representing a periodic signal, but for non-periodic signal, we normally use Fourier transform. And because in communication system, we don't know what kind of signals we're going to get, so Fourier transform will be very useful. And because most of the time our signals are non-periodic, okay, random in nature, just like my speech, what I say. And lastly, we're going to take a brief look at the signal. How is it transmitted through a linear system? So the communication system we're going to study here are basically linear systems. Okay, all right, let's start with the types of signal. So I believe you already learned this from the very beginning of your study. So signals are categorized into two types. One is the analog signal and the other one is the digital signal. All right. So as far as analog signal is concerned, analog signal are signals that are continuous in time and amplitude. All right, meaning the signal can appear at any time, can last for as long as it wants, and also the amplitude can take any value. All right. And for digital signal, the signal are basically discrete in time and amplitude. That means the signal only appear at a certain time, lasts for a certain duration, and the amplitude also can only have some definite value. All right, it cannot have any value. So as far as the signals are concerned, right, the easiest thing to see the what kind of signal it is by looking at the waveform. All right. So here we have four types of signal. All right, mainly different they are different in the manner where some are continuous in time, some are discrete in time, and amplitude as well. Some are discrete, some are continuous. So the first example here are signals that are continuous in time and continuous in amplitude. All right, so most real life signal are actually continuous in time and continuous in amplitude. That means the signal can happen and occur can at any time, all right, last for any duration. The amplitude can be any value, can be very low, can be very high, So that is a continuous time and continuous amplitude signal. And the second type of signal here is the continuous time and discrete amplitude. So continuous time meaning the signal is continuous over time. All right. It appear and exists for as far as time is concerned for the entire duration of the time, and the value will change. Okay, but the value the amplitude of the signal actually will change, but then because it's discrete, in this example here, the amplitude only are allowed to exist in two values. All right. So this is discrete. Discrete meaning it can only hold certain values. So in this example is two. It can be more than two. Yeah. Um, the third type of signal is discrete time and continuous amplitude. So discrete time meaning the signal will only exist at certain time. Yeah. So in this case, you can see the signal only exists at certain time. All right. And then the amplitude is continuous. So that means the signal can take any amplitude. All right. The last one here is a discrete time and discrete amplitude signal. So that means this signal only exists at certain time, and the amplitude only carries some fixed value here. All right. Again, in this case, we have only two different values for amplitude. All right. Um, So that is for the types of signals that we have. Um, then the next thing we need to understand a bit is on the properties of the signal. All right, I believe you have learned this as well. So these are all revision. Okay, the first type of property is called periodic. All right, uh, what is a periodic signal? So a signal that is periodic is when it repeats itself after a fixed period of time. All right, so these are called periodic signal. So example of a periodic signal is a cosine signal. All right, that where the sinusoidal waveform keep repeating itself over time. And non-periodic signal like this kind of random wave or random signals are non-periodic. Okay, so again, in nature, most signals are non-periodic. That is a real life signal. Then another way to describe a signal, the property of a signal is to say whether it's even or odd. All right. In signal processing, even and odd signals are quite important actually. So how do we know whether a signal is even or odd? So by definition, all right, a signal is even if it can be reflected in the axis at 0. So meaning if you look at this one, all right, if I were to 0 meaning is along the vertical axis here, right? So meaning if this signal is symmetrical on both sides, yeah, then this is an even signal. For odd signal, if all right, if the signal at by definition here x at when the time at is minus t is actually the negative version of the signal at time t, positive t. So if you look at this one, this is a sinusoidal wave. All right, so at time they say this one here is positive. All right, that then on the other side, when the time is negative, then the value is negative. So that is a odd signal. Okay, so that is for periodic, even and odd. So the type of what else? Did I miss something? Okay, never mind. All right, so the next one we want to look at is the transformation that we usually perform on signals. All right, the first one is reflection. All right, reflection meaning we actually reflect in this example here, we reflect the signal uh, along the vertical axis. All right, so we kind of flip lah. Right, another way to put it is to flip. So the positive become negative, the negative become positive. So this is reflection. And a very important signal transformation in communication system is the shifting. All right, shifting meaning if you look at this example, we have a rectangular pulse that center at t equals to 0. But if you were to shift this signal in time, right? So in this, we can have this signal. So this is a signal that has been shifted in time. All right. So if you represent this signal in using equation, if this is xt, then the shifted version of xt in this example is xt minus 2. All right. That means we shift the entire rectangular pulse, all right, to the right hand side of the time axis. All right. So this is shifting. And then scaling is we actually stretch or compress the signal. All right. So let's say if the signal originally looked like this, if you were to compress it, all right, so it become narrower. All right. So as far as equation is concerned, if this is called xt, then this will be x2t. Yeah. So we multiply t by a number that is greater than 1, you basically compress the signal. But if you want to expand it, in this case, it's called expansion. We expand the signal when we multiply the signal, the time by a value that is less than 1, then you actually stretch or expand the signal itself. So this is scaling. Okay, so here I have an example. So in this example, what kind of signal transformation that has been performed here? From A to B. From A to B. What kind of transformation happened? Hello? Can someone answer, please?
Yes.
Yeah. So what kind of transformation here?
Shifting.
Yeah, shifting. Good. And here, because the signal has been shifted to the left-hand side, so you can see as far as the equation is concerned, I don't know whether you can see, I think it's a bit small. Last time, this one, when this slide is being presented on the in the lecture hall, the screen is very big, so everything is blown up. But now I think it's a bit small for your, I don't know about your screen. Okay, so it's plus here because it kind of shift to the left hand side. If you shift to the right hand side, then it's minus, as this one. Okay, so let's move on to learn the different types of system. Okay, so what is a system? Okay, first of all, what is a system? A system basically is a circuit, right? Or it's a circuit or any block that actually process input signal to produce sets of output signal. All right. So we actually call it that the output signal is a transform version of the input signal. All right. So this system actually perform some changes on the input to produce a output lah. Yeah. So the changes that it does, the system does, is called the transformation. All right. And if you were to put it in mathematically, the output yt it can be is equal to the t times xt, where xt is the input signal. And what is t? T is the transformation function of the system, right? You learn this one, right? Okay. So as far as our communication system is concerned, right, we are going to study three subsystems, which is the transmitter, the transmitting system, which in most likely most of the time is a modulation system, and the channel, because the channel makes some changes to our signal as well, and also the receiver. All right. So each of these subsystem actually transform its input signal into a certain form. All right. So so we're going to study, as far as this course is concerned, we need to learn all these three main systems and how these three systems actually transform our signal. Okay, types of system. So again, there are many ways to differentiate or to describe the properties of a system. So in this case, we have two very simple one. One is called continuous time. The other one is called discrete time. Okay, so for continuous time system, as the name suggests, this system process input that are continuous and also produce output that are continuous. Okay, very easy, straightforward. Continuous in what? In time. Yeah, that's why it's called continuous time system. And for discrete time system, right? Discrete time system are system that process input and output signal that are discrete in time, right? That's why the first thing before we learn the system, we need to know the signals. That's why I need to define earlier on what is discrete time signal, what is a continuous time signal, right? Then this kind of system is called discrete time system. Okay, and what are other properties of a system? All right, so okay, sometimes you can see some definition that say, oh, this system is causal. So what does causal mean? All right, a system is causal if the output at any time, all right, only depends on the input value up to that time, but not the future value. All right, makes sense, doesn't it? So that is causal system, and in fact, a lot of our system nowadays, or a lot of the present system are causal. All right, unless you want to talk about system that depends on input in the future. Well, how would the future value come in at the moment? So as far as the system is concerned, the system that we're going to study are actually causal system. So yeah, the output only depend on the input values up to the time that we're interested in. All right. Linear. How do we know whether a system is linear? All right. A system is linear if the output of the scale sum of two input signal is the equivalent scale sums of the output. So what is meant by here? Okay, take for example, I have an input called x1. All right, this input after it goes through the system produce an output called y1. All right, it perform a transformation on the input and then produce an output y1. And I have another input which is called x2. All right, so the system will produce an output that I call it y2. Okay, and a system is linear. A system is linear. All right, if the output of the scale sum of the two inputs. So in this case, all right, so if I were to perform some changes on the input, which means I multiply the input 1 by a factor of a, and I multiply the input 2 by a factor of b, all right, and then I send it into the system. So I send the sum of these two input into the system. So what will produce basically is you can see that the corresponding output for each signal will be again multiplied by the same factor. So x1 I will get x1 that produce is no x1 that cause the output of y1 will be multiplied by a factor of a, and then y2, which is the transform version of x2, because x2 has been multiplied by a factor of b, y2 would be multiplied by b as well. So a system that create this kind of output is called a linear system. Okay, time invariance. The next property is called time invariant. Time invariant meaning the system is output is the same, all right, given the same input regardless of time. So meaning if I give one input at time equals to 0, all right, and then I give the same input again at time equals to 5. Right, so the system is invariant if the output that it produced at these two different times is the same. All right, so that is very important again in communication system. All right, if I transmit a signal in the morning, I transmit the same signal again in the afternoon. All right, you should receive, or the receiver should actually receive the same signal. All right, the same set of signal. So that is for time invariant. So it doesn't matter when I put the input in, all right, as long as the inputs are the same, the system should produce the same output. Okay, so this is very important for communication system. But again, it may not be true. Yeah, some system may not be able to do it, like satellite. Okay, so here, this slide actually tell you the difference between time invariant and time varying. So as the name suggests, yeah, time invariant meaning the system will produce the same output regardless of what time you put the input in. But for time varying system meaning the system will produce different output when you put in the same signal at different time. All right. So that means I put in a signal in the morning, I receive a certain output, and I put in the same signal again in the afternoon. The system give me a different output. All right. So if that's the case, then the system actually is called a time varying system. All right. So how do we represent but as far as are concerned, if we prefer to use a time invariant system. All right, we prefer to use a time invariant system. And of course, when you design a system, you have to make sure that your system is time invariant. All right. So as far as our course is concerned, we'll consider only the time invariant system. So how do we actually represent time invariant system? All right. So we can actually represent it mathematically by this equation for continuous time. And for discrete time, we actually use this equation. All right, so what it means is, if you look at this one, x t minus tau, that means I actually do a shift, right? I actually shift the input by amount of tau. So I put into the system, the output actually is a shifted version of the output when when t is 0. Okay, I just shift it by amount of tau, that's all, the same amount. All right, so again, this is a shifting properties. So this is for continuous time. For continuous time in the equation, you see that we always use t. All right, but for discrete time, we use n. All right, n means the sample at a certain time. Yeah. So this is for discrete time. So again, you can see that whenever you shift the input by k, then the output also is a shifted version of the output at n by k, right? So it's the same shifting occur at the output. So as far as our course is concerned, all right, we are going to look at only the linear and time invariant system. All right, meaning the system is linear. When the system is linear, that means we can make use of this superposition theory here. All right, so we add two signals, the system should give me the sum of this output of the two signals. All right, so that is linear and also time invariant, meaning the performance of the system is not going to change over time. So I actually give it a abbreviation which is called LTI. So LTI stands for linear time invariant. Okay, just to complete it, stable system. How do we know whether a system is stable or not stable? All right. So a stable system is a system that take bounded input and produce bounded output. All right. So a good example would be this pendulum. If we have a pendulum that actually hang at the top, then when you actually swing this pendulum, it's actually stable, right? It's stable in the sense that you wouldn't swing out of the highest point where it was started. But if you have an inverted pendulum in the bottom case here, all right, you actually mount the pendulum on the floor, all right, and you release it from any height, you see that it won't swing, it will straight away fall. So that is called unstable system, because um, the output you know that it definitely it go down, it won't actually swing. Okay, feedback system. The system, okay, I think you know about this also, right? In the feedback system, in certain system, we actually send part of the output or the entire portion of the output back to the input and added to the input itself. All right, this is called a feedback system. So in some communication system block, we do use feedback as well. Okay, so that is feedback. Okay, next thing is about the signal energy and power. So how do we actually measure the energy and the power of a signal? All right, so if we have a signal, let's say passing through a resistor, and normally our load is resistive, right? So we can actually represent and then load by a resistor. So the instantaneous, this is called instantaneous, meaning the power at time t. The power at time t actually, again, this is something you learn from year one. P is equal to VI, right? So it's the product of the voltage of the signal at time t and the current produced by the signal at time t. Okay, this is current flowing through the resistor and the voltage that we measure across the resistor. So that is power. And we can also write it in the form as V square over R, right? V square T over R, yeah. Why V square T over R? Because I is equal to V over R, isn't it? Okay, so that is power. And what is energy? So energy, to find, if you know the power, to find the energy, basically you need to integrate lah. Yeah, and how much energy? Total energy. If you want to find the total energy between two intervals, T1 and T2, so that means you need to perform integration, all right, of the power with respect to time. So if you were to replace the equation for power, then you find that you basically need to integrate v squared t over r. Yeah. And in this case, if you were to divide the results of this integral by the duration, where you actually perform the integral on, all right, that will give you the average energy within this duration of time. Okay, so how do we actually apply this concept on continuous and discrete time signal? So as far as the continuous signal is concerned, all right, for total energy, we actually again take the amplitude of the signal, we square it, and then we integrate it over the time that we're interested in. That will give us the energy. All right, and then for discrete time actually is the same thing. So instead of taking t, using t, we use n, right? Because we use n to represent the discrete signal at different time. Yeah, we use n to represent. So again, it's the same. So so instead of taking the integral, we actually take the sum. So we add all the square of the amplitude of the signal. All right. And if you want to get power, then we just take the energy, we divide it by time, then we get our average power. Okay, so basically this is how we calculate um, signal energy and power. When we come to that part in our course, then I'll put in some numbers and show you how we actually do the calculation. Okay. Right. So this slide basically will show you the energy and power over infinite time. All right. Um, so as far as infinite time is concerned, then that means we need to take our integral or our summation from minus infinity to infinity. Duration. All right. So again, by knowing the nature of the energy in the signal, we can actually define what kind of power the system has. Okay. So we have two important subclasses of signal. We have signal that has finite total energy. All right. So these are the signals that actually where the total energy converge. All right, so this kind of signal will give us a zero average power. However, if we have a signal that has infinite total energy, then the power, we actually define the power by the finite average power. Okay, and as far as our study is concerned in this course, all right, we are going to analyze a lot of time, analyze the signal power, um, and we are going to analyze also the noise power. All right. So again, we'll come to it lah. Okay. Okay, so this slide actually show you why do I want to this slide? Oh, okay, because I want to describe the property. Okay, so here this slide actually show you that the sinusoidal and the exponential signal properties. So periodic signal, this is applicable to periodic signal. All right. And in here, I actually give you an example, which is a sinusoidal wave. Okay, so a sinusoidal wave basically is a signal that run forever. So it's infinite. All right, so you can see that the total energy is also infinite. All right, but here I actually show you because of its the total energy is infinite, then we get average, the finite average power. All right, so in this example here, we actually compute the energy over one period, and then we divide the energy over one period by the time, which is a period, then we get a value of 1 here. Okay, so this is useful when we have a harmonic signal. All right, so what is harmonic signal? Harmonic signals basically is when you have a signal. All right, so the signal may be consist of a multiple signal. All right, so it may have the harmonics. So it's useful for that purpose. So again, when we come to it, then we use it. All right, so here this slide will again we define the unit impulse and step signal. Okay, unit impulse, especially impulse signal. Impulse signal is very useful in analyzing the communication system block. Okay, so let's do some revision. I think this is recap, but you learned it before. Okay, discrete. This is discrete unit impulse signal. Is defined as because this is discrete. I start with discrete. Okay, we start with discrete. So discrete, we write it in n. All right, xn is equal to delta n. All right, and the value is 1 only when n is equal to 0. Okay, so this is a very important definition for the discrete unit impulse signal. And then for any other value of n, which is not zero, the amplitude or the magnitude of xn or delta n is 0. Okay, so if you were to draw the waveform or the signal on picture, then you can see that when n is equals to 0 here, all right, you have an impulse, you have a short impulse, and then the magnitude is actually 1. All right, and then the unit step signal. Unit step signal is defined as, you normally use U to represent. All right, so UN, the value is 1 only for all n values that is greater or equals to 0. So that's what it means. For all values of n that is greater or equals to 0 here, then the magnitude of the UN is actually 1. All right, so because this is discrete, so therefore you the signal only appear at all the corresponding value of n. N equals to 1, n equals to 2, n equals to 3. So n has to be an integer value. Okay, another way of looking at the unit step, the discrete unit step signal is you can look at it as you have a running sum of all the impulse. All right, you have many unit impulse response. That is starting from 0. You have pulses along the way. Okay, for all the n values greater or equals to 0. And for continuous meaning continuous in time. All right, so again, it's very, very similar. So instead of n, all right, again, this is continuous. So instead of using n, we use t. So xt is equals to delta t. All right, and delta t will have a value of infinity when t equals to 0. So you only have a unit impulse at t equals to 0, and it's 0 for all other values of t. All right, and we normally use an arrow here, arrow, and then the area, actually the area is 1. All right, if you were to, but then because it's so narrow, so the value is infinity. Then for continuous unit step signal, all right, so this is a step signal. All right, this is a step signal. So by definition, ut, again, instead of using un, we call it ut because t represents the continuous time signal. So the value is 1 when t is greater than or equals to 0. All right, and for t less than 0, the value is 0. So that is for unit step signal. You can see it's actually, this is for continuous. So you can see that it's continuously 1, right? But for discrete, then you see that the value is 1, or the output is 1 only at certain time. All right, where all the n values here. So it's not continuous in that manner. Okay, so next thing you need to know is on convolution. So this slide basically reintroduce what convolution is. All right. Okay, convolution process actually take an input signal, return an output signal based on knowledge on the signal's unit impulse response Hn. All right. So what we need to do is basically to know the unit is impulse response. So what we do is we actually send a unit impulse into the system as input. All right. And then we look at the output. And then the output, we actually call it Hn. All right. So this is the definition for Hn, which is called the unit impulse response of the system. How the system responds to an input of an impulse. Okay. So the idea behind convolution is we're going to use the system's response to impulse, all right, to calculate the units or the system's response to a more complex signal. All right. Why we can say that? Because this is only applicable when our system is linear and time linear. All right. This is applicable when it's linear. So linear, that means it actually satisfies the superposition property. Okay, now let's take an example here. I have input. This is again discrete input xn. All right. So xn basically is a sum of various input. Okay, for different n values. Okay, I add up all the value of x at different n. Okay, and then I multiply. This is a multiply with the coefficient. All right, and I combine all these signal. That actually is my xn. Yeah. So if I were to expand the equation, then I can expand it as a1 x1n, a2 x2n, and so on. All right, and yn, which is the output of the system. Okay, I can actually represent the equation or by, again, this is a sum of a sets of output. All right, again, this is discrete, so I represent it, I use a sum to represent. So if I able to expand it, this is the sum of y1 and y2, y3, and so on. All right, multiplied by the coefficient a. And then what is y1? Y1 basically is the system's output for input x1. All right. So if x1 is multiplied by a1, then the y1 will be multiplied by a1 as well. Okay. So let's take a look at how we actually come out with the convolution theory. as far as our signals are concerned. So now I'm going to use a set of discrete input signal, xn. All right. And this xn, basically, I write it at a linear sum of set of input impulse signal. So what it means is x minus 1, all right, multiply with delta n plus 1, all right, will only give me an output of x minus 1 when n is minus 1. All right. Why is that? That is because delta n plus 1 is only 1 when n is minus 1, right? Because delta 0, if you go back to the definition for impulse signal, all right, delta 0, when n is 0, so that means delta 0 is 1. When n is not 0, any other value of n, which is in the bracket here, for any other value that is non-zero, the output is always 0. All right, the signal is always 0 here. So that means for this delta function to be 1, so this n has to be minus 1. All right. So when this is 1, only I can get my x minus 1. All right. If n is not minus 1, then the delta function will be 0. So 0 multiplied by x minus 1, you always get 0. All right. So for any n values not minus 1, all right, then there is nothing here. So basically, I can represent this signal x minus 1 by this expression x minus 1 multiplied by delta n plus 1. All right. Similarly, x0, all right, x0 will only, if I were to multiply with the delta function, all right, then the value will only be x0, all right, when the n for that delta function is 0, right? Because delta 0 is 1, yeah? So the next one, same thing. For x1, I need to multiply with the delta function n minus 1. All right, delta n minus 1. Because delta n minus 1 will only give me a 1, all right, when n minus 1 is 0. So n minus 1 is 0 only when n is 1. All right. So again, so when this is 1, this will give me x1. And this only happen when n equals to 1. All right. So, so what I can represent this signal, basically xn, I can represent it by x minus 2, delta n plus 2, x minus 1, delta n plus 1, and so on. All right. So that means in general, I can actually represent any discrete signal xn using this equation. Right. So this one actually make use of the shifting property of the delta function. All right. I shift the delta signal or the delta function by k value. All right. For all the k value in x. Okay. Example here, I have a discrete signal xn that is represented by this waveform here. Okay, so I have a pulse at this is what, n equals to minus 4. All right, I have another pulse at xn equals to minus 3, one at n equals to minus 2, 1, and so on. So this I have pulses for all these value of n from minus 4 to plus 4. So if I were to decompose this discrete signal xn, all right, basically I can represent this pulse, all right, with this expression for n equals to minus 4. All right, for n equals to minus 3, which is this pulse here, okay, I represent it with this signal, with this expression. All right, so this n xn, basically I can write it as let me see. I can write it as x minus 4, right? And delta n plus 4, and then plus this term, plus this term, plus this term, and all the way up to this n equals to 4 here. Okay, and yeah, that is how we actually decompose the or decompose the discrete signal, okay, using the delta function. All right. So as far as the study of a system is concerned, all right, so we actually need to analyze our system by studying the output signal when the unit impulse signal is used as the input. Yeah, this is a repetition of what I mentioned before. All right, we put in unit impulse signal in a delta signal into the system, and we see how the system responds, and then we take the output as the Hn, which is the system's unit impulse response. Okay, and so we can actually use this to infer the property about the system structure and its behavior. I believe you learned this as well from which course? I can't remember which course you learned. Okay, so now there are three types of unit impulse responses that we can have from a system. All right, so by looking at the how it responds to my unit impulse input, we actually can determine the property of the system. So in this example, number one here, the system is causal. Why causal? Because there is nothing until the time where n is 0. All right. So n less than 0, we do not know how what it's like. So we can also know that when n is not is less than 0, we got nothing. So stable means what? Stable means you can see that the response of the system actually kind of decreasing. Okay, so it's stable, and it's also finite impulse response. Finite meaning again, it actually go down slowly. Okay, we know that it's so our response actually is finite. So we'll look at another example infinite later on. Yeah. So in you can see that in infinite here, all right, the response of a system never go down to 0. Then that is infinite. All right, it never go down to 0, then it's infinite, but it's getting smaller. Okay, it's getting smaller. That's why it's still stable. But if the response keep increasing for increasing n values, then you can see that the system basically is unstable. All right, because if you keep increasing with n values, you never know it's going to blow. All right, and of course it's infinite because the response keep increasing as well. Okay, so that brings us to